the last but not least speaker of today is Sanja Atanasova, who is an associate professor in the Faculty of Electrical Engineering and Information Technologies at the Saints Cyril and Methodius University in Skopje. Her main research activities are in the field of Fourier analysis, functional analysis, and integral transforms. Sanya is also a member of the European Women in Mathematics Association, and her talk has the title Integral Transforms Through the Prism of Distribution Theory. So Professor Atanasova has the word.
Okay. Thank you very much for the nice introduction. First, I would like to thank the organizers of this webinar because it is not easy in these difficult times to organize any event. And also, I would like to thank them for inviting me to be a part of it. It was nice to see different women for different type field of interest and research. I must say, at the moment, I'm a mother of a 6-month-old boy, and it was a quite challenge to make this presentation as it is. So I will start. So my presentation, or I will present my work of interest. Actually, this will be a result of several papers published in the recent years. As I was introduced, my field of interest is functional analysis, especially generalized functions or distributions, integral transforms, and asymptotic analysis. So the outline of my work, of my talk, will be the following. First, I will introduce the distributional theory, just to feel the idea and the need of such a theory. And then I will talk about the asymptotic analysis, but this will be done through integral transforms. And at the end, I will present my work and my obtained results. The theory of distributions was introduced in 1950s when Schwarz published his book on generalized functions, and since then they have found many applications both in science and engineering. What is interesting about distributions is that they can be viewed, the discontinuous, for example, functions can be easily managed as continuous and differentiable functions. The theory of distribution somehow was introduced before, when the direct delta function was introduced. We all know the direct delta function, and this function actually is not a function in the ordinary sense, because it's not Lebesgue integral, and also this symmetry property does not, which is satisfied for the delta function, does not hold for ordinary function. So in order to introduce this function, from now on it will not be a function, but in order to introduce it, we must change the way we see of functions, or with other words, we need a new concept. There are many ways how the distributional theory can be introduced. For example, there is the sequential approach, the approach of Mikoshinsky, Bremerman approach, but maybe the most used one is the functional approach. This was actually introduced by Schwarz. So what is done here? We take operations on ordinary functions such as differentiation or Fourier transform, and these are extended by first writing them on in the language of functions for ordinary functions, and then using them to define this operation on distributions, and then using these operations as easily as for ordinary functions without making any confusion on where everything goes. So first, I will need the space of all continuous and differentiable functions on open set omega, with the derivatives existing up to order n. So the first test function spaces d of omega will be a subset of all smooth function where the topology is defined with the seminars defining here. So test functional spaces is actually a space of functions, and as I said, we will need the operation first to be defined on some functional spaces and then extending them to the spaces of distributions. So distributions in our approach, our functional approach, will be defined as continuous linear functionals on test functional spaces. For D, the space of distribution will be denoted by D prime. And when we think of distribution, we think of something that maps D to the field of complex numbers. And this will be symbolically written with these Japanese brackets. We read as F acts on P, where P is an element from the test functional space. Here you have two examples. First one is the delta distribution, but shifted by point x0. And it is defined in the following way as the value of the P at the point x0. And these are very easy examples. And the second example is the Heaviside distribution, where it is defined as the integral from 0 to infinity dx dx. So what is the difference between two examples? The second one is actually a locally integrable function. And in that way, if we have a local integral distribution now, we can define the distribution not using these Japanese brackets, but through this integral here. Those distributions that are locally integrable and can be defined in this way are called ordinary distributions. Another space that is mostly used in my work is the space of test functional spaces, and also the space and the appropriate distribution space is the space of temporal distributions. First, we will need functions that are rapidly decreasing. This will be called all the smooth function for which this supremum is finite. And the space endowed with this topology is called the space of Schwarz-test functional spaces and is denoted with S. Actually, what are these functions? These are functions that decays at infinity faster than any polynomial. One such an example is the function e to the power minus x squared. So the space of all continuous and linear functional over S is denoted by S prime and are called temporal distribution or distribution of flow growth. No matter what approach is taken to the theory of distribution, one quickly concludes the distribution in general do not have a value at a point. So one way to overcome this problem is in the sense of Lojashevich, where he take equals between a distribution and it considers it locally equal to some continuous function. But more general approach to this problem is the asymptotic analysis and generalized asymptotic. This asymptotic analysis is mostly considered or studied by Russian mathematicians Druzhinov and Zavialov. Also, there is a nice book of Estrada and Campbell, and in the recent years, a lot of on this problem is done by the Novi Sad group of mathematicians led by Filipovic. So, in Also, in the recent years, there are a lot of papers where this asymptotic analysis is studied in through the prism of integral transform, such as the Laplace, the Wavelet transform, short-time Fourier transform, Radon, Wavelet, and etc. So first I will need to introduce some integral transforms that I used in my presentation here, just to feel the sense of why or they are needed. So I'll start with the Fourier transform, which we all know, and it's one of the most used transform in signal processing, and it takes what is done by the Fourier transform. It takes information from time domain and transfers it to the frequency domain. But the problem with the Fourier transform is that it does not reveal how the signal frequency content vary with time. So, for example, it is not suitable for analyzing non-stationary signals. So, one way to overcome the problem with the Fourier transform is by introducing a signal, a window G, with the fixed length that glides through the time axis t and performing a time localized Fourier transform. This leads to the concept of short-time Fourier transform. So the short-time Fourier transform of a function f with respect to a window g will be defined in the following way. Here, x denotes the translation parameter, c denotes the modulation parameter. Maybe the most cited book on short-time Fourier transform is the following book of Groheny. So the short-time Fourier transform is good, but because of this fixed window, the problem is that some things need to be predefined, which leads to a poor time frequency resolution. So one way to overcome the difficulties, the problem with the short-time Fourier transform is to introduce the Wavelet transform. The Wavelet transform is defined in the following way, where we have a translation parameter and also we have the duration. So the difference is that we have here some kind of scaling, and this duration parameter actually works in a way that if you have some signal, the duration zooms in or zooms out on some certain part of the signal. But the problem with the Wavelet transform that these basis functions are actually self-similar, and they are overlapping in the frequency domain. So there is no straightforward way to turn the scale information into a proper frequency information. So in 1996, it was introduced another transform, the Stockwell transform, defined in the following way, and it is considered some kind of mix between the short-time Fourier transform and the Wavelet transform. So what this transform does, it takes a signal and it decomposes it into temporal and frequency components. And the frequency component adjusts the size of the window, which is the problem in both previous transforms, and realize multi-resolutions over different frequencies. This means high resolution leads to higher frequencies, a lower resolution leads to lower frequencies. This means that the Stockwell transform is not invertible, but on the other hand, it extracts the exact time and frequency information of the signal without needing the reconstruction formula for the signal. And maybe the problem is the redundancy, but in the recent years there have been a lot of papers that try to overcome this problem. And the last integral transform that I'm going to use is the directional short-time Fourier transform. This transform was introduced by Giff and something, and here we have the translation and the modulation parameter, but we have another parameter u. This is actually the directional parameter, so we have some kind of direction, and u is an actually element from the unit square. We will talk about it more later. So the first results that I'm going to present are the results from two papers that were published this year. The first one is characterization of waveform set by the Stockholm Transform, and by me, Professor Filipovic, Krangovsky, and Saneva. And the second one is covariant theorems for the Stockholm Transform of resulting distributions by Saneva, me, and Beta Bralia. So first, I will need an appropriate spaces that I'm going to work, as I already introduced S and S prime. And also, I will need this test functional spaces S0, which is the space of highly time frequency localized test functional spaces over the real line. This is actually a closed subspace from S, and what this means, an element is from S0 if it is from S, and also all its moments are equal to 0. The dual space S0 prime is called the space of resulting distributions. So because the Stockholm transform is a transform with two variables, we need to define the space of S on Y. This is the space of all smooth function for which the norms defined here are finite, and the dual space is S denoted by S prime. So Y is only used shortened for R times R minus 0. For the Stockwell transform, similarly as for the Wavelet transform, I will need some kind of admissibility, and that's why for function C we will say that this reconstruction window for G from S if the following admissible condition is satisfied, and then I have a nice reconstruction formula, which means that if I know the Stockwell transform of some function or some signal, I can easily reconstruct the signal using the following conversion formula. And just in old theory, when it's introduced, when I have the inversion formula, I always check the Parseval relation, which it holds, and for my transform, it has the following look. Where C, if you see here and here is this admissibility, some kind of constant that is finite, so we are okay with the definition. When you have also a reconstruction formula, one can define a synthesis operator for integral transform. For us, the Stockholm synthesis operator is defined here. And as it turns out, the synthesis operator is actually a formal transpose of the Stockholm transform. This means that the composition of the Stockholm transform and the synthesis operator gives the identity. So the main results of the second paper are those two continuity theorems. The first one says that the Stockholm transform maps a signal or function from S0 to S on Y, and the second theorem says that the synthesis operator also is a continuous map from Sy to S0. So when we have these continuity results on test function spaces, we can extend the definition of our transform to the spaces of distributions. And this is actually done with the following definition. The first one says that the Stockwell transform is an element from the dual space S prime and Y, and this action is given with the following act. And we say similarly for the Stockwell transform, for the synthesis operator, it is defined on S prime of Y into S0 prime with the following definition. Actually, this is called the introduction of transform on dual spaces by duality approach. And one quickly concludes that both transforms are continuous linear maps on the appropriate distribution spaces. So now, when we have the theory of on distribution for this transform, we can perform asymptotic analysis on it. So there are several papers which are referenced here when some of where different asymptotic analyses are given. Maybe I can, the most of them use Tauberian and abelian type results. I will say what are abelian, what are Tauberian type results. When you have something that goes in one direction, that is abelian type result, and Tauberian type result is when you have int and only if. The first two papers are about the Wavelet transform. The first one also is a vector value distribution, but it is a more general result using the Wavelet transforms. And the third and the fourth paper are about the short-time Fourier transform. Actually, these are my papers. My maiden name is actually Kostadinova, so these are more papers from 2013 and 2016. So to make the asymptotic analysis, first I will introduce something that is called slowly varying function. And we will say that L is slowly varying at the origin, and respectively we will talk about at infinity if it is a measurable real-valued function defined on these intervals here, and for which the limits here are exist and are equal to 1. So a distribution F, we say that is quasi-asymptotic, that has quasi-asymptotic behavior of degree alpha at the origin, and respectively we have at infinity if there exists a limit distribution H such that the limit here exists and is equal actually to this limit distribution H. These here are only short notes for this limit at 0 is equivalent to this notion here, so short notion, and this one is for at infinity. I have several results. The first result is of abelian type. We say that if L is slowly varying function at the origin and F is a distribution from S0 prime that has the following quasi-asymptotic behavior, then for its Stockwell transform, we can say that the second result is of Tauberian type, and we say that if for a distribution F and a window function G, the following two conditions are satisfied. The first one is that these limits here exist, and the second one is that the Stockwell transform satisfies this type of bound. These two conditions are necessary and sufficient for existence of a limit distribution H such that the F has quasi-asymptotic behavior. Also, two more results. The difference between the previous abelian type and this one is how the Stockwell transform behaves in both variables. If you see in the previous results, we have some kind of behavior on B by epsilon, where epsilon is very small, and for A, and for this we have another type of behavior. So if distribution F has this has asymptotic behavior, then for the Stockwell transform we can say this, and we have a similar covariant type result presented here. So the second paper that was published this year was a characterization of a wavefront set by the Stockwell transform. First, what are wavefront sets? Actually, wavefronts are something that characterize the product of two distributions. Actually, as for the value of a distribution of a point that is not always defined, we have a similar problem when you have a product of two distributions. So here you see the definition just for illustration of two distributions. For example, the product is well defined when you have the two smooth function. The product is well defined when you have disjoint singularities of the distributions, and etc. But not always the product is well defined. So the wavefront set provides a condition where the two distributions have a product. So more or less, when you see at the product of distribution, you need to impose some kind of decay properties of both functions in order this integral here to be absolutely convergent. So to do this, first we'll need something that are called nice point or a regular point. And we say that the point BA is regular directed of some distribution U if and only if. First, there exists a function phi from a distribution from G prime such that the value of distribution at the first variable B is equal to 1, and the second condition is that there exists a conical neighborhood V such that this behavior is of this defined, or the Fourier transform of F times U decays at mostly polynomial. So the wavefronts are actually the complement of the set of all regular directed points. So in the recent years, there are a lot of papers that characterize the wavefront set of distribution using integral transform. Actually, motivation of our work is the last paper of Filipovic and Vuletic, where they characterize the wavefront set using the Wavelet transform, and this is they describe their regular directed points through the decay of the Wavelet transform, but a parametrized Wavelet transform by introducing a family of parametrized wavelets in a fixed cutoff function. More general result is actually the result of Bell and Fucher, where they analyze the wavefronts by using Wavelet transform, but introducing a more general dilation group. So, as you see, the first two papers that I was talking is using the Wavelet transform, and the Wavelet transform is actually good when you want to catch, for example, singularities of a function, but the Wavelet transform does not say where this singularity occurs, or they don't give information about the geometry of the singularities. So there are other transforms that are more suitable. For example, Candace and Bonanko introduced the curved transform and discussed the wavefront set that catches singularities that are in the form of a curve. Or, for example, Kipiniok and Labate used the Wavelet transform, which gives information about the singularity and also the orientation of the singularities. Filipovic and Frankovsky also used the work of Formander, and they used the wave concept on micro-local analysis. And there are a lot of other papers here, just a review on what is happening at the moment on this field. So we will work on more general Stockwell transform as we work for quasi-asymptotic analysis, and we will need a multidimensional Stockwell transform that was introduced in the PhD thesis of Riba, where he used the following definition. So let me see the whole slide. As you can see, okay, this is the definition of the Stockwell transform of a distribution of a temporal distribution F. The window G that is here satisfies the following admissible condition. And also in my work, I will need this relation between the Stockwell transform and its Fourier transform. So the Fourier transform of the Stockwell transform. If you see in the definition here that gives the multidimensional Stockwell transform, we have the translation parameter, we have the modulation parameter, but here are some matrices RA, which are defined in the following way. So, as you see in the slide, there are 4 matrices defined for dimension 1, 2, 4, and 8. These are all rotations for matrices that are in the group SO on N. This is the group of all invertible matrices. They are not uniquely defined. Actually, you can change the sign before the elements, but this can be done for all the rows. Only for the first row, this is not allowed. So they are not uniquely defined. And also, the most important thing is, again, I cannot stress enough that the dimension is only allowed for 1, 2, 4, and 8, because we need the map from A to RA to be continuous. This we need because we need some change of variables in the results, and continuity is very important. So this is only possible in these dimensions. So although I will not give here, but the rest of the paper actually tries to resolve this problem by taking pairs of, for example, if I want to reconstruct something for n equals 9, I make permutation of, for example, 9 ones or 2, 2, 2, 2, 1, and etc. So the wavefront set for us, for these dimensions, is defined for windows, for family of windows G lambda, where G lambda is connected with G in the following way. G is actually an element from S. The support of the Fourier transform on these our window functions are in some called ball with center En and radius lambda r. We will need a conic G with a vertex and A0, and this type of conic neighborhoods. So, what is our definition? Our definition says that if F is a temporal distribution, then the wavefront set can be defined as the complement of all G microlocally regular points, B0, A0. That is, we say, as I said, the wavefront is a complement of these regular points. So we say that a regular point does not belong in the wavefront of the distribution if and only if there exists a smooth function phi different from 0 at x0, there exists a cone gamma, there exists a lambda from 0 to 1, such that for all n bigger than 0, there exists a constant which depends on n, for which the Stockwell transform behaves in the following way, or is satisfied the following bound. The second one is equivalent definition, where I use this relation of the Fourier transform. Why the Fourier transform of an integral transform? Because I will need in the definition of the product, I need the Fourier transforms of the distribution to be well defined. So the main result here is that our Wavelet transform actually coincide with the Commander wavefront set of distribution f from S prime. Okay, and also there is another result here there in the paper that the same is actually done and is more exhausting to be followed. That when I work on Sobolev type spaces, also I obtained a wavefront set that is that coincides with the Hermann wavefront. So now I make a little a big generalization on the work by introducing function g h, which where h is an element from this index set ek, such that gh, the Fourier transforms are smooth functions. They are bigger at 1, bigger than 0, so they are positive, and for which the support contains in the support does not contain 0. So for generalization, my window function g will be actually a product of this how I say partition functions. So our generalized Stockwell transform is defined in the following way, where we have the integral of f and defined by this new partition functions or windows gh. Now the connection or the Fourier transform of our Stockwell transform is given with the following relation. So more general result is presented here. First one, we'll need the definition of our new wavefronts with respect to this generalized Stockwell transform. So if we have a distribution, temporal distribution, then the wavefront set of f is the complement of all g micro-locally regular points, or we will say that that the point b0, a0 does not belong to the wavefront if and only if, again, there exists a smooth function different from 0 at x0. There exists a cone that is a subset from this partition of Rn done in the following way. We must avoid 0 because G is not defined to 0. The support does not contain 0. There exists a lambda from 0, 1, such that for all n bigger than 1, there exists a constant Cn for which the Stockwell transform behaves in the following way. So this is a more general result, and actually the second result that I'm presenting here states that our wavefront set coincides with the Formander wavefront set in a way that we avoid problematic points which contain 0. And just see how much time I have left. Okay, so the second or the third part somehow of my talk is to present another results published in 2016 and both papers published last year that are using the directional short-time Fourier transform. So first, I will need briefly. I will need another type of test functional spaces in appropriate distribution spaces. Now, if you remember, I used y in the previous for the Stockwell transform for r times r minus 0. So the first part for the Stockwell transform for the quasi-asymptotic analysis, I work in r, and then I extended everything for wavefront set on Rn. And here for the directional short-time Fourier transform, I'm working on general things, so we work on Rn. So just short notion for this, the unit sphere times R times Rn, I will use y on power 2n. So the test functional spaces S on y to n will be the space of all smooth functions for which these nodes here defined are min. So if we have a locally integrable function f on yn, we say it is of slow growth if it satisfies the following bound, and we will always identify an element. We always identify f with an element from the dual space with this integral here given with 1. So motivation for our work is actually are actually two papers. The first paper is from Grafakos and Sanson from 2008, where they merged the radon transform and the time frequency in very natural way, and actually introduced the concept of directional sensitivity. So first they introduced these double-rich functions, where they use translation, modulation, and they use this parameter here that gives the orientation. But we actually use the definition of GIF, and this is actually the second paper that we are based on, where they where he let the directional parameter only in the window G. So if you see the difference here, this part is omitted, but this is specified using it's easily shown that you can use the more simple structure of these rich functions, because this relation between the Wavelet transform and the short-time Fourier transform is satisfied. So this is one row that gives that we can go from the definition of Grafakos and Sansing and the definition of TIF. So our directional short-time Fourier transform then gets the following look given with again, we have a nice reconstruction or inversion formula for reconstructing every single signal by using the directional short-time Fourier transform, and this is given with 25. And we have a nice directional synthesis operator that is also transpose of our transform. Again, this means that the composition of both transforms gives the identity. We have a nice continuity results for the directional short-time Fourier transform that says that this is continuous from S to S on yn, y on 2n, and also that the synthesis operator is a bilinear, that's continuous bilinear mapping from S to the or S of y on 2n into S. We have extended the definition of the directional short-time Fourier transform on the spaces of temperate distribution. Similarly, as for the Stockwell transform, this is done by duality approach. Immediately follows that both transformations are continuous on the appropriate space of distributions. and that both are also satisfying the inversion formula given in 21. So these are similar results as for the Stockwell transform, but we need them to make asymptotic analysis for the temporal distribution, but now in the words of the directional short-time Fourier transform, and we will need another kind of asymptotics. Now we will use the notion of quasi-asymptotic bounded, and we will say that the distribution is a quasi-asymptotically bounded of degree alpha at the origin with respect to a slowly varying function if the following bound exists or is satisfied. Shortened notion for this here in the sense of the weak topology is this one. So maybe only one result I will give. We will say that distribution F is quasi-asymptotically bounded if its directional short-time Fourier transform performs this type of asymptotics. And okay, maybe a few more results. The paper that is was published recently, actually, the last one of that gives the directional regularity of a distribution using the directional time frequency analysis. Actually, this is also a result that discuss the Bayes-Ron set, but in the words of the directional short-time Fourier transform, but not on the spaces S, but extending the results to the space K1. This is actually the test space of all exponential distributions, or K1 will be the space of all smooth function for which the topology is defined with the following norm, and the dual space is actually the space of exponential distributions. So one will say that K1 is actually a smaller space than S, so exponential functions are less in number than the polynomial one, but when you have a dual space, K1 prime is actually bigger than S prime, so somehow how the results are more general. And also when you work in S, the nice thing is that the Fourier transform maps S to S, and it actually is isomorphism from S to S, the Fourier transform. But when you work with exponential distribution, then the Fourier transform does not take an element from K1 and goes to K1, but actually it takes a function and it maps it to analytic functions, and this is the space actually U, where U is defined in the following way. These are all functions for which the norms are defined here, and they are only defined on these bands TK. The dual space is U prime, and because the directional short-time Fourier transform is an transform with two variables. First one is from K1, the second is from U, and the tensor product of those both those spaces is defined here. So this is, and the dual space is the following one. And we have an identification as previously from an element from the tensor product with an element from the dual space, and this identification is done with the following relation. Actually, it is important to see that these are actually analytic functions that are with respect to the second variable, and it's not very easy to look into what is happening there because it does not transfer an element from R to R. So so we need a more deeper results when proving things from functional analysis. But when you see it on the slide, it looks like it is similar because the story goes in a similar way. We need the continuity result. We need definition to be extended on the space of distributions by duality approach. But when we work for wavefront set, we will need a multidirectional short-time Fourier transform, and we will extend it in introducing actually the multidirectional or k-directional short-time Fourier transform, where k is an element from 1 to n. Actually, the case when k is equal to 1 is actually discussed in the previous slides, and we need several notions. For example, we need the tensor product of K1 completed in the P or epsilon topology. And also, this is notion for the Dirac product of K1. So this is the notion for tensor product. These are notions for Dirac products. We will need more general elements from the unit sphere, and we'll have a vectors u to the power k as a vector from un to uk, where all of them are independent vectors from the unit sphere. And we need the notion g to the power k as a product of g1 to gk, all of them as elements from k1. So when you have some kind of generalization, the directional short-time Fourier transform will be defined with the following integral. When we have split the direction that we work in, so we don't work with one direction u, but we split the directions when we catch singularities to different to vary on different sides, un to uk. So okay. We have the reconstruction formula, we have the synthesis operator that is defined, and the most maybe important theorem that is given here is actually one of the crucial theorem of our work, is that the one that connects the multidirectional short-time Fourier transform with respect to different windows. Here we have g to the power k or h to the power k, or something that if someone works in this field, that is important that when you work with wavefronts, the transforms that are some kind similar to the short-time Fourier transform must be chosen in a way that they don't depend on the choice of the window. The difference with the Wavelet transform is actually that the Wavelet transform depends on the window and are more hard to be managed than the one that does not depend. So for our wavefront, I will need several more notions, just quickly to go through them. Again, case from 1 to n. We have some hyperplanes that are given here, and we have a definition of our wavefront. F is temporal distribution. We said that F is k-directionally regular point at this hyperplanes. If there exists a window g to the power k, a product of open balls and a cone for which the following relation is satisfied, this means that the supremum of our short-time Fourier transform decays with respect to c at most polynomially. It does not depend on the choice on the first variable. And what is the result here is that our wavefront is closed in this set here rk times rn. And maybe I will finish here. Thank you very much for your attention. So if you have any questions, please do not hesitate to ask.
Okay, Thank you, Professor Atanasova, for the very nice talk. Very interesting. So I let audience, if they have questions, to ask you directly. There are no questions. There are applauses, I can see.